My guest today is Joseph Hickey.
Hi, Tom. Yes. So today I'd like to talk about um, research on station level temperature records in Canada. And with an eye to the question, is Canada warming? What do um, the most basic measurements of temperature across the country show us? And so I'll show you what our research on this topic is looking like at our research organization, which is called Correlation Research in the Public Interest. And the link is up there on the slide. And Correlation is a not-for-profit organization conducting research, scientific research in the public interest. And we're based in Canada. And I'll just tell you a few words about the organization. Go to the next slide here. When you go to our website, you can see there's a section that's called research, and it has a list of all our research papers. And the paper that I'll be talking about today is one that I wrote and posted in December of last year, so about a month ago. And it's called Artificial Stepwise Increases in Homogenized Surface Air Temperature Data Invalidate Published Climate Warming Claims for Canada. And just to give you a bit, we'll go into that paper in detail in the presentation, but just to let you know what other topics Correlation has been working on. It's been mainly all-cause mortality analyses of mortality during the COVID period. So we've done a lot of epidemiology, and we've taken a position, and we've found results that are quite contrary to the dominant paradigm or the dominant narrative about COVID. And so you can read all about that in our many articles on those topics. And that can all be found on our website at the link at the bottom of the page there. But for today, it's going to be about temperature data in Canada. And just a few words about myself. I'm an interdisciplinary scientist. I have bachelor's, master's, and PhD degrees in physics. And my PhD was in a sub area of physics that's called complexity science. And essentially, it's applying physics analysis and modeling methods to topics that are perhaps not traditionally considered physics. And so there are a lot of models and statistical analysis methods that are done in other fields like epidemiology, geosciences, medicine, and many other, even social sciences. And that was actually a large part of my PhD thesis, was about the formation of social hierarchies and also studying the statistics of legal citation networks in the legal system. So all that to say that I have an interdisciplinary background. After finishing my PhD, I was hired to work at the Bank of Canada, Canada's central bank, doing agent-based models of economic systems. And I have one paper, if you look on my publication list, that is about a model of firm competition and how market shares evolve in the economy. And so that's to give you a sense of the interdisciplinary background that I have, rooted in a physics training. And while I was at the Bank of Canada, I was asked to research temperature data in Canada. And at the bank, they wanted to compare how economic activity may have been affected by potentially changing climate conditions. And so as part of that, I was tasked with studying the temperature records for Canada from Environment Canada's official database. And as I was doing that, I noticed something very strange, which is a feature in the temperature records that I'm going to talk about today in this presentation. And so that's where this research comes from initially. And so those are a few words about me. I also just mentioned that I, in fact, lost that job at the Bank of Canada because of the Canadian government's vaccination mandate that was applied back in 2021. And so I was one of the people who refused to be vaccinated, and that ended up resulting in the end of that employment. And instead, now I'm working for Correlation, doing independent research in the public interest. And so all that to say that I have spent a lot of time looking at temperature records in Canada and found a very interesting feature in the data that is a stepwise increase in temperatures. And I'll get to that in a moment. And just to give a bit of an overview of the data that's used in this paper, it's surface air temperature data for individual stations in Canada. And that data comes from a data set that Environment Canada produces, which is called the Adjusted and Homogenized Canadian Climate Data. This is important because whenever you have a temperature record at an individual station over a long period, like many decades, there's always going to be breaks in the data, discontinuities. And that could be because at some point in time, the station was moved from one location to another. And so then it could even be a change in altitude. And so you'll see often a noticeable change point in the temperature record when you take annual averaged temperatures. And there can also be gradual biases that affect temperature records from many, many different factors, and that can be broadly grouped into features like changes in the land use and land cover in the vicinity of the instruments. It can also have to do with changing the instruments, the measurement instruments, or even or calibration issues affecting the measurement instruments over a long time, or it can be from changes in observation procedures. And so scientists working at national meteorological institutes like Environment Canada spend a lot of time studying these different types of biases and trying to make adjustments, which has been the subject of a lot of articles, including a lot of critical articles about these adjustments that they make to the temperature records. So that's the basic data set that I'm using. And the paper also contains a number of emails from Environment Canada that I have obtained through access to information. And they are emails where that involve me when I was employed at the Bank of Canada and studying the temperature data. And I noticed something that seemed very unusual in the data. And so I was asking the senior researchers at Environment Canada how this could be. And so the emails that contain their responses are shown in this report that I've done for correlation research in the public interest. So that's the basic data for the paper is Environment Canada's temperature data and the access to information emails. Now, the main point, the main feature of the paper that I said is something unusual or something noteworthy is what I call a stepwise increase in the annual average temperature for individual stations. And so here, this graph shows data for Moncton, New Brunswick, which is in the eastern part of Canada, near the Atlantic Ocean. And the graphs show the annual average of the different types of temperatures, daily temperatures that are measured at the station in Moncton. So actually what they measure is the maximum for the day and the minimum for the day. And then the mean for the day is the average of those two things. And so with those three quantities, you can plot the annual average. So the left graph over here is the annual average of the mean temperature for the day. And you can see that it hovers around a low plateau for a number of decades up until one point in time where it suddenly jumps up to a higher plateau, and it stays at that higher plateau. So this is why it's a stepwise increase. It's hovering around a low plateau for several decades, and then jumps up to a new plateau and stays there for several decades. And this is what I call the 1998 step. So this is the main feature that I want to talk about today. And to give some quantification of the size of this step at 1998, what we can do is take those same graphs from the last slide and look at the average for the lower plateau. So it's the average of the annual values that are in blue, and do the same thing for the upper plateau, and then just compare the difference of those two plateau values, and you see that it's around a degree Celsius in magnitude of a step upward. And so that's a large step. And we see this for many stations. Here are a few examples of other individual stations. These ones are all in the east of Canada again. And you can see that this step is observed for these different stations, and always at the same time in 1998. And continuing just a few more examples, Eastern Canada, and then moving more into Central Canada. You have this step happening in 1998. And then going further into Central Canada, go further west toward the center of Canada. Now, to look at how this step feature might be spread across the country, I applied a method where I calculated the difference in basically those red lines that I was showing before, the average over a certain number of years on the upper plateau minus the average on the lower plateau. And so in this graph, I've used a 5-year window on either side of the break, where so you have from 1998 to 2002 inclusive on the upper plateau, and then 1993 to 1997 on the lower plateau. Take the average for those two sets of years and then subtract, and that's the step size. When we do that, we see that well, the circle size on this map is proportional to the size of the step, which I call delta S. And the color red is for circles that have a step that's larger than 1 degree Celsius. The black circles are for stations that have a step size between 0 and 1, and the blue circles are for stations that have a step size that is negative. And so you can see that across most of Canada, there is a positive step in annually average temperature, ranging from the east through the center of the country and into the west and what we call the prairies in Canada. And then conversely, on the west coast, there is no step. If anything, is slightly negative, and the step essentially disappears in the western part of the country. And just for reference, Moncton, New Brunswick, which I had shown before as an example, is here in green. So you can see that there are many other cases that are similar to Moncton or have even larger steps. So that shows how widespread this step is across the country and its geographical organization, with a difference on the west coast and in some parts in the north as well. And another thing we can do is look at how unique is this step in time. And so to do that, we applied a method where I redid this break analysis for every possible year since 1948 and up until 2018, which is the extent of the data set that I used for this. And so 1948 is the starting year because that is the year when Canada had wide coverage, the widest coverage of temperature stations. Prior to that, there was very little coverage in the north of the country. And so 1948 is the year that Environment Canada typically uses for its climate trend analyses for Canada. And so what I've done here is redone the break analysis for many different years, testing whether there was a break in each of these years. So was there a break at 1960, 1970, and so on. And when you do that, you have many stations, and so you have a distribution of step sizes. And so 1998, which corresponds to the map that I showed on the previous slide has a distribution that looks like the one in black here. And so what you can see is that there are a lot of stations in 1998 that had a large step, as we've already seen on the map. But this graph allows us to compare with other years, and you can see that if you take another year, for example, 2005 in purple here, the distribution looks quite different. It's more centered closer to zero. It means that it's not a particularly abnormal or interesting year in terms of doing step analyses. And so by doing these distributions for many different, but like candidate break years, you can make a plot where you take some characteristic of the distribution, for example, its mean or its mode, the position where its peak is located, and plot that as a function of time. So if we take the average for each of these distributions that correspond to different break years, then you get the black line on the left panel here. So you can see that basically the only year that sticks out as far as having a large mean of this distribution, so a distribution that looks like this black one, is 1998, with a small influence from 1997, and that has basically just to do with overlap of how we're determining where to put the break here in this sliding window. But this graph with the black line with a peak around 1998 shows that this step of 1 degree Celsius of magnitude, which is widespread across the country in that year, is unique in the temporal record. So it's really a special feature. It's not something that happens every 10 years or so. Here I've done the same analysis that I was describing before, but with a refinement to take into account the noise that can be present in the data when you think of year-to-year annual average temperature fluctuating around either the lower plateau or the upper plateau. So what we've done is we've taken the step size between the two plateaus and then scaled by the standard deviation, actually the average of the standard deviation for the two plateaus, to kind of give a relative measure of the step size relative to the noise in the data. And so doing this, it gives essentially the same result, but it highlights a bit more where the steps are largest. And also draws out a little bit more the lack of a step or even a slightly negative step on the West Coast. And doing this, repeating the same analysis to see whether or not this step is unique in time, gives a similar result again. And so 1998 really sticks out as being a year where there was this unusual large stepwise increase in temperature. And the fact that it's stepwise is important because it's not as though there was a single suddenly warm year followed by a gradual increase in temperature. Instead, it is a sudden increase to a new plateau level where the annual average temperature stays at that plateau level going forward. And that's the next point, is that there is no warming trend for most of these stations across Canada since 1998. And so just as an example, to show what I'm talking about, this was Ottawa, the graph from a previous slide. You can see that after the step in 1998, the temperature is not increasing overall. If anything, in this case, you might see a slight decrease. So to check how the trends look after 1998 across the country, I have done this analysis, which is also in the paper. And so in this case, I applied the analysis method that Environment Canada uses to determine trends, which is the method of SEN with a statistical significance test applied by Zhang. All those details are described in the paper. But the point is that when you look at the trends post 1998, there are essentially no statistically significant trends for individual stations. Those are the X's mark on this map here. The blue X's show trends that are negative although not statistically significant. And the red X's show trends that are positive but not statistically significant. So, and then there are two stations where you have a statistically significant positive trend. But basically, you cannot say that there has been warming at the station level in Canada since 1998. That's what this graph shows. And right, so we've gone over the fact that there's a step in 1998 and that there's no warming since 1998 in Canada. And what that means is that, and I'll get to this in a moment, but it basically means that all of Canada's warming since 1948, when there's good data, would have occurred in a single year. And so that's very interesting, and it's incompatible with the paradigm of warming caused by anthropogenic CO2 or CO2 in general. And so I'll get to that a little bit more in a moment. But I also wanted to mention that another feature of the report from December is that the access to information emails with Environment Canada show or include an email from another Bank of Canada employee, Julien McDonald-Guimond, who had been working with the data, the temperature data for Canada, and noticed something strange, which is that in many cases, the minimum temperature for the day was larger than the maximum temperature for the day, which is impossible. And so Mr. McDonald-Guimond had actually gone through the data set and prepared a large table of all the instances he noticed where the minimum daily temperature was greater than the maximum. And he sent that table to Environment Canada and asked them to explain how could this be and what should he do with the data to be able to work with it. And so, and that table is included in in an appendix in the report, Appendix F.2, and the reference for the papers at the end of these slides. And so, when you take those examples of days where the minimum temperature is supposedly greater than the maximum, and you make a graph of the number of occurrences of the gap in temperature, so take the difference between the minimum and the maximum. And we have, as you can see, quite a few examples of quite large differences, actually. So the median is a 0.8 degree higher minimum than maximum. And it can go up to even as high as 30 degrees in one example, as you can see on the tail of the graph. So this is kind of an example of how, when Environment Canada makes its adjustments, how it can produce some absurd or incorrect results from doing this. And then a big part of the reason for doing this, or for that this occurred, this problem occurred, is that Environment Canada has adjusted the minimum temperatures in their data set by shifting them upward because they believe that they've assessed that there is a bias in the minimum temperatures because they changed the time of observation of temperatures in 1961 at the most important stations, including airports. So this is kind of a side point in that this in the paper because it is in the access to information documents, but it's an interesting point. And as you can see in the box here, when Environment Canada was informed of this, they responded that they were quite surprised by the frequency of the issue you reported. And so you can read more about that in the report as well. And then getting back to the main point of the paper, which is this stepwise increase in temperature in 1998. What it means is that all of Canada's warming would have occurred in a single year. And so this graph is from Environment Canada's paper of 2020, Vincent et al. 2020. And what they show on the right panel is the annual mean of, the anomaly for the mean temperature, which is for all of Canada. So used, they've done a gridding process and come up with a single time series for that is supposed to represent the whole country. And when you look at this, you see again the step at 1998. And so that is coming from the steps at the individual stations that I showed before. And what I did was to take this graph and digitize the data, which is easy to do with online tools now. And so this is what I've done is reproduced their data from their graph and then reproduced their trend analysis for that data. And so in their paper, they quote a 1.74 degrees Celsius increase from 1948 to 2018, based exactly on that graph. So I've reproduced that using the same method that they use. And that's the green line here. And just to add another way of doing the trend, the red line shows the linear least squares fit. And now, since we know that there's this very unusual step at 1998, it makes sense to say, what would the trend look like if that step had not happened, if it didn't exist? And so you can adjust the data to remove the step. And the way that I did that is to simply take the average of the points on the graph from 1948 to 97, which is the solid purple line down here, and the average of the points from 1998 to 2018, which is the dashed line. And then lower the data from 2018 by an amount equal to the difference in the two purple lines. And so when you do that, you remove the step, and that's what's shown in the right panel. And you can see from looking at it that there's no trend on the right panel. And then when you apply the trend analysis methods, what you find is that there's no statistically significant trend for Canada since 1948 if you remove that step. And so that's important because that really shows that all of Canada's warming since 1948 occurred in a single year. And now in the paper, I argued that that is a sign, because this 1998 step is discontinuous, that's a sign that this could be due to a measurement artifact of some kind or another. Could be that they changed the instruments in the span of a year widely across the country, and it happened that in 1998, Canada was joining the global climate network for the first time. And so that was one hypothesis, but it could also be due to natural climate variability, but not due to warming driven by adding CO2 to the atmosphere. So we are exploring a correlation, other hypotheses that relate to natural causes for this step. And one of the main candidates that's coming out is oceanic oscillations of sea surface temperature. There's very interesting oscillations where the temperature in the ocean, either the Pacific or the Atlantic, remains warm for about 30 years or so, and then suddenly switches to a regime where the temperature is colder and stays that way for around 30 years. And so you can see on the screen some graphs of these oscillations, and that's coming from the chapter by Dalio and Easterbrook, and the references at the end of the slides. And interestingly, right around 1998, in the mid-90s, there was a switch in the Atlantic multidecadal oscillation to a warm state. So the Atlantic became warm suddenly, right around the time of the step that I've been showing for the land temperatures. And at that same time, the Pacific switched to a cold state. And that is the only point in time since 1948, which is the period that I've been analyzing, where the switch in regime for the two oceans happened at the same time. So the mid to late 90s is an important time in terms of this flip of the Pacific becoming cold from its warm state down to a cold state, and the Atlantic going from a cold to a warm state. And that could explain potentially why we had the cold more like the lack of a step and even possibly a negative step on the west coast of Canada and a larger step in the eastern part of Canada. And so this graph is also from the chapter by Dalio and Easterbrook, and it shows that there's a correlation between the Atlantic multi-decadal oscillation and land temperatures in some places. So especially in the northeastern part of North America, meaning that when the Atlantic is warm, the land surface temperatures were generally warm over the period 1948 to 2007 is what this graph is for. Now, the next thing I've done to investigate this hypothesis a bit further is to look beyond Canada into the United States, Mexico, also some European countries here, but I'll focus on North America and applying the same type of step analysis that I showed before for the map of Canada, but here now we're including stations from the rest of North America, essentially. And this is a different data set. This is the Global Historical Climate Network data. But it's a similar result. We can see the step is present across much of the northern part of North America, but not on the West Coast. And even as you go down on the Pacific coast, down into Mexico. And the other graph is, again, the similar analysis, but now controlling for or adjusting for the noise in the data. And we see it draws out a bit more the blue circles on the West Coast and shows maybe more widespread increased step for the eastern part of the continent. So this is very interesting. And again, this step this is now for the United States. And we see again that it's a unique feature. It's 1998 where the distributions of step sizes really stand out as being large compared to any other year. So that is those are the points that I wanted to make. The takeaway, I think, is that Environment Canada claims that there has been a 1.74 degrees Celsius increase in temperature in the country since 1948. And that is, I'll go back to the graph here, that is based on this graph, which has a clear step in it. And so this trend is based on, this is not a suitable analysis for this type of data. You have to acknowledge that it's flat and then it has a step and it's flat again, rather than saying rather than trying to fit a model that is based on a slow linear increase, gradual linear increase. And so if you're a policymaker that is concerned with carbon dioxide, you have to think, does it make sense that all of the warming in the country would have happened in a single year? And you have to think about, is that really caused by adding carbon dioxide to the atmosphere, or could it be due to something else? And I think it's quite possible that it's more due to oceanic oscillations that are affecting land temperatures. And so that is the essence of what we've done so far. We're continuing with this research, and we want to study this more and see where it takes us in terms of understanding how temperatures have evolved in Canada and where they might go in the future. Because if you look at these oscillations, if the pattern holds for the Atlantic oscillation of about 30 years, we're right at the point where that you would predict that would flip to its cold state. And so we might be in for a few decades of colder winters, in fact, going forward. And so we would like to see what kind of analyses we can make on that basis in our work as we go forward with our research. And so if you'd like to read more about our research, this is our website, correlationcanada.org. And these are the references as promised that are cited in the paper and in the presentation. So that's, do you have some questions, Tom?
Yeah, I do. First, just an observation that's just super interesting and great work. I just love what you've done here. Do you think that there's any chance that would be stepwise warming, but more gradual cooling as these ocean temperatures flip? Or would it also be stepwise on the cooling side?
That's a good question. It's not something that we have. It's something that we would like to look into for sure. And but I don't have an opinion on that for the moment.
Yeah. And we don't really have good enough data to look for other steps that go way back beyond, 100, 200 years ago, anything like that?
Well, that again, what I've done is I've focused on the temperature records at the stations, which go back in Canada. Some of them do go back to the late 1880s. As you go beyond, like the further back you go in time, the fewer stations you have, and the quality becomes more questionable. But that kind of time span is what can be studied with this type of data. And so that's what we're focusing on now, because it's a rich, large data set, and we're going to see what we can get out of that first before we try to do anything else.
How big of a deal do you think it is that you pointed out there the 10,000 plus instances where daily min was higher than daily max?
It's a big deal in that it shows the impact that the adjustments can have. They can be quite absurd. Now, in terms of how it affects the data set, these are individual days in a data set that spans many years and has hundreds of stations. So it turns out that those 10,000 instances are only about 1% of the total data. So it's not something that affects the data set very much. It's more of an illustration of what the adjustment procedures can do. And it causes you to question what are they doing, and why are they raising the time series for the minimum temperatures, like from 1961 to present, shifting it upward. And is that valid to do that? So that's important to question those points.
And then you said there was one possible hypothesis that they changed the way of measuring, that they rolled out new stations or something in 1998, but it looks like that probably wasn't it, huh?
Well, the kind of assumption in my report was that since these are discontinuous changes, these must be artifacts. There's a lot of examples in the scientific literature where when there's a discontinuous change in an annual average temperature record, it's considered to be an artifact. And even Environment Canada themselves, in a 1999 paper where they were preparing one of the earlier versions of their official data set, adjusted and homogenized temperature records, they applied an algorithm, a procedure, where they said that if there's ever a step that is of magnitude 0.6 degrees Celsius or larger, we will absolutely adjust that record without even having any documentation to show what it was. So you can see that the approach has been to take these discontinuous breaks as being artifacts, because there are so many different ways that those artifacts can be introduced into the records. But we think now that there are some compelling possible natural explanations for this shift. That being said, this shift, which is very important and very real, is not compatible with the CO2 warming paradigm.
So separately, have you looked much at just the impact of urbanization over the last 70 years or something on the whole temperature record?
No, that's not something we have looked at. Um, the there are some um, adjustments that are made by Environment Canada, um, although not related to urbanization or urban heat island effect, in fact. But that is a field that is has a lot of literature, and those would be more gradual changes, like an increase of a gradual warming bias. Um, so that would not really relate to the stepwise increases that actually, when you look at the graphs that I showed, um, explain all the warming for Canada since 1948. So that's an important thing to study, but it's maybe not that crucial in this question of whether we can say Canada is warming or not overall.
Okay. Any other points you want to make before we go ahead and finish this one up here?
No, I think that is everything. I just encourage people to take a look at our website and see the research we've done. We are independent of government, of any corporations. Any funding we receive is from individual donations, and there's a donation page on our website if you feel like supporting our work. And we're producing a lot of reports, and we have lots of interesting projects on the go going forward as well. Oh, also, we have a free newsletter where we update people about our work, and that is on Substack. So if you find us, there's a newsletter section of the website, or if you can also go and find us on Substack, Correlation Research, and get linked up that way.
Okay. And as usual, I will put, if it's okay with you, I'll put the PDF of your slides up on my Substack and put a link to that from the show description.
Yep, that would be great.
Yeah. And then if people want to contact you, it looks like there is a contact form on your website. Is that a good way?
That's a good way. Yep.
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 Okay.
Yeah.
Okay. I would love to have you on again if you have more presentations, because that was really good. Thank you.
Sounds good. I'll just mention my email also is on the front page of the report itself. So if you, that's another way to contact me.
Perfect.
So,
yeah. All right. Joseph Hickey, thank you very much for doing this, and we will talk to you later.
Thank you very much.